So who had a chance to take a look at or at least skim the paper? I realized as I was going through it again that there were a lot of stumbling blocks just in the basic definitions that made it really hard to understand, like unnecessarily hard to understand. And so I thought maybe the first thing I could do is just go through some of the definitions and just clear things up, because it seems like they define things in really weird ways. And it ended up, and I recall now that when we were going through this paper, it ended up taking us like 6 weeks to get through this one paper, because we would fight over what they actually meant by what they said. And I realized that if you guys are reading this for the first time, you're probably running into all those stumbling blocks. And so I think maybe I could help you guys just by kind of just walking through what they actually mean by what they say.
That would be great.
Yeah, sounds good.
All right. Is it okay if we start? I just kind of just jump straight into things. Okay. Oh boy, causal fusion is down. That's really sad, because a large part of my my presentation is on causal fusion. So, but I do have. Okay, so I do have this, and so so the first thing that we should probably talk about is, so I mean, everyone's kind of familiar with the notion of identification, right? We've all taken the course, all taken Robert's course, and so when we say we're identifying something, it means that we can predict from the observational distribution what the interventional query is, right? And so I just want to remind folks of what the do calculus actually does. And so there's basically just 3 rules. And the thing that's really interesting about this paper is that it doesn't use the do calculus directly at all to actually prove, to actually identify a causal effect. But then it turns out that you can use the ID algorithm that was presented to prove that the do calculus is complete. And so I just want to remind folks what the do calculus is. It's just 3 rules. The first rule is about ignoring observations. And the way to read this is that, and if you guys are looking at Spitzer's notation, he has this p sub x, which is really the same thing as probability of y given do x. Okay, the reason why they did it initially this way, they hadn't invented the do notation yet. And it was really to indicate that the observational distribution P is different from the interventional distribution X. So I'm just kind of like, this kind of a little notation thing that might have caught you guys if you're like, what's going on, right? This doesn't look like anything that I've seen before.
Hey, Jeremy, quick question.
Yeah.
Just for people who kind of are seeing this for the first time, like what's the objective of what you're trying to show us here?
Oh, so the objective of, are we recording yet? I should just check on that first.
Yeah, we're recording.
Okay. Yeah. So the question is that if I have a probabilistic query, and let's give you an example. And of course, they're all in causal fusion, and causal fusion is still not going up. But so let's suppose I have some causal effect here. So here's a DAG. I've got X, I've got Y, and then I've got this bidirected edge, okay, which is indicating that there's some unobserved confounder that is causing both X and Y. And what I want to know is I want to know the probability of Y given do X, okay, and I want to do it from just observations of X and Y, just the observational joint distribution of X and Y. Even in the presence of this unobserved confounder, okay? And so the do calculus tells us that there's a certain, or if you just remember backdoor path, right? Backdoor path says, if I have some observed confounder, then I condition on the observed confounder, and that gets me the causal effect, right? So you could think of the backdoor path as an adjustment formula, right? You just, you sum over the covariate, the Z covariate, and you're fine. And what we recall is that not all covariates are safe to condition over, because because if you condition over Z that happens to be a common effect, then you get a collider, right? And so then you end up biasing your predictions, right? So you have to know when it's safe to use the backdoor path. So you have to know when it's appropriate to adjust for confounders and when it's not. And so the backdoor path is one rule for adjusting for confounders. But there are other ones as well. There's the front door path, if you guys remember what that is from the class. And unfortunately, causal fusion is still not going up, which is really sad. But in that case, you have some mediator between X and Y here. And it turns out that in this case of X going to Y, when there's an unobserved confounder, this effect is not identifiable. So it's not actually possible to predict the causal effect of X on Y when you have this unobserved confounder. If you could measure this unobserved confounder, then you could do it. That's backdoor path. But if you can't measure the unobserved confounder, you're just going to be unbiased. The front door path says, well, if I have some mediator here, Z, that is between X and Y, and it is not confounded by our unobserved confounder, U, then there's another adjustment formula that we can make that would enable the, hi, Zizia. You want to get the Lego movie working? Well, if you bring the pad down here, I can start it for you if you'd like. Oh, you want to watch on the big TV? You want to ask Mommy? She's still sleeping.
I think she still wants us to sleep
a little bit longer. Do you mind if I take a quick break to take care of this situation here, and then I can return? Would that be all right?
Go ahead.
Yep, sounds good. Yep.
Okay, sorry. I'll be right back. 5 minutes.
While waiting for Jeremy, can someone paste the link to the paper for me? I don't know which one that we are looking at.
So there is a spreadsheet where all the papers that we have checked before.
Okay.
But I don't remember where it is.
Is it pinned? I think if it's pinned, I should be able to find it.
I think it's
yeah, it's pinned.
Fourth last. Yeah. I can pin it for you.
Oh, let's see. Okay.
You got it?
Yep. Thank you. Yep. Yep.
All right. Let's see if causal fusion's working. No. Is anyone else getting causal fusion to work?
Let me check.
Should have emailed Elias, say, hey, I'm using your software today. Can you make sure it doesn't go down? Oh, well. Okay. So these are all the figures where it doesn't work, and these are all the figures where it does work. Okay. So what we were talking about was situations where you can identify a causal effect and situations where you cannot identify a causal effect. And the algorithm that's presented in this paper is able to not only figure out whether...
Jeremy,
yeah.
Since we had a hiatus, actually, I just had, I think a few people just joined.
Oh, good.
Do you want to just start from scratch?
Yeah, sure, no problem.
Give the overview of what problems being solved and kind of what you're going to cover today.
Sure. So,
Jeremy, you know, my causal fusion is working.
Oh, good. Huh.
Maybe switch browsers.
I could switch browsers. That's not a bad idea. Try Opera.
Opera. Yeah. Yeah, I guarantee you a bunch of graduate students at Columbia have not optimized for Opera.
Oh boy, do I even know my password? I'll just let it keep going. Oh, no, wait.
Try to be, oh.
Yay! Okay. So we got it working over here, and even if it's not on Chrome. Maybe I have to like, wonder if like clear the cache or something. I have to do something like that. Okay, so if I go to projects, ID algorithm, okay. Load. Check. And load. Oh, it's currently on the oh, good. All righty. So as I was saying, if you recall the front door path, right? So remember the typical smoking. Okay, let me back up. Okay. So what we're going to be talking about today is the identification algorithm, the ID algorithm that came from this paper, Identification of Joint Interventional Distributions and Recursive Semi-Markovian Causal Models. So we'll explain what all those terms mean. And this is interesting. So if you guys recall from Robert's course, you remember how to predict a causal query, an interventional query. So you're predicting a query from an interventional distribution, but you're only using data from an observational distribution. And we had the backdoor path where if you had a common cause, then if you adjusted for that common cause, then you could get an unbiased prediction of the causal effect between X and Y. And if you had an example where you were not, so in the case where this, if you recall the smoking versus tar versus cancer problem, so you want to know the causal effect of smoking on cancer, and then Philip Morris says, hey, the reason why you see this correlation between smoking and cancer is because there's this, and don't forget this was the 50s, so they couldn't do DNA sequencing. They said there was this gene that caused you to crave nicotine and also causes you to be more likely to get cancer. And so people who don't smoke aren't really attracted to cigarettes, but they also don't have that gene that causes them to be more to get cancer. So that's why you see this correlation. And therefore, we can't distinguish between the genetic effect and maybe the direct effect of smoking on cancer. And so, you're basically screwed. And so now if you could observe this genetics component, if we could do DNA sequencing, then we could use the backdoor path adjustment formula to predict the causal effect of smoking on cancer. And if you use the front door adjustment, then even if you don't have, and so the other way of showing this is with this bidirected edge. And so if you just kind of go back and forth between an unobserved confounder and a bidirected edge, they really mean the same thing. But the other option is if you have a mediator that is shielded from this unobserved confounder, then you can also predict the causal effect of smoking on cancer. And so if I go causal effect of smoking on cancer in causal fusion, look, they've got the same kind of Spitzer notation here, where they have the do rather than having probability of cancer given due smoking, they have probability of cancer in the interventional distribution where we intervened on smoking, right? That's just the other way of representing that. So if I were,
Jeremy, you saw that, I think you mentioned that notation, because we use that same notation in counterfactuals, right? Is it different? Is it different?
It's different because the subscript is not on the probability, it's on the variable themselves. So I would have cancer sub smoking, which means that this is the probability of getting cancer in a world where smoking has been done to it, right?
I don't understand this.
Okay.
Notation you're talking about is the
subscript
is on the.
Yeah, let me just show you the difference between the two, right? So in counterfactual notation, we have the probability of y sub x given x prime comma y prime. Right? So in this case, the subscript is on the y variable. Right? And I should actually just make that little lowercase y, right? So we're saying we're getting a number, and that number is the what we observe is right. This is counterfactual notation. This is a slightly different notation.
You can write it again as like without the condition. So let's write a few variants of it just so we're clear.
Oh, sure.
Like we also have probability of y sub x given x, which just equals, which is just
y, right? Exactly, y sub x, right?
Sub
and that
x.
is actually the same thing as the same thing as probability of y given do x.
Then we can also write probability of,
which is the same thing as probability of x of y.
Okay, so this Spitzer notation puts the x in front. In front of the
probability.
That's confusing.
Yes.
Because Jansing and Peters, their notation puts the x in the superscript. And I was like, oh man. Okay. That's okay. That's useful to have as a reference.
Yeah. So these three are equivalent. Probability of y given do x is the same thing as probability of y. Probability of y in a world where we do x. Probability of y given do x, and the probability of y in an interventional distribution of doing x. Then these are all the same. So, so now that we have, now that we've kind of defined that, there's a few other things that I think we should probably just kind of recollect. So if you recall, so we've already figured out the interventional, we already figured out, so we were just back on the backdoor path here, right? And so if I go derivation, so it actually already calculated for me. So if I want to predict the causal effect of smoking on cancer, probability of cancer given due smoking, that's actually equal to this probability distribution right here. And then notice that this is entirely in terms of observable variables, and there's no need to include the genetics in there. And so the question is, how did they get this formula? And so there's actually a derivation of it. And so what we're going to talk about is what this means. And so summing over tar, we can understand that, right? Then it says C component form, and we'll get to that and why that we'll get to that initially, because we'll define what C components are. And the main idea here is that you can always factor a joint probability distribution in terms of the observable variables. You can always factor it into a couple of into a product of C components is what they're called, and these C components are in terms of the interventional distribution. So what this means is that you can factor probability of cancer given do smoking into smaller pieces that you can then solve independently and then multiply together. And that's really the main idea behind the ID algorithm.
So the C component form is really just a factorization.
It's a factorization of the original interventional distribution. That's right, in terms of the confounding components. And so this kind of divide and conquer approach is the key to the ID algorithm. You get nothing else from this whole discussion. Just that's a good take home, is that we have a method for factorizing an interventional distribution that makes it easier to solve. Okay. Okay. So we have this intervention. So we have the front door path, and we have a derivation. And what I claim is that by the end of this, but if you've read the paper, if you haven't, but you've just skimmed it, whatever. By the end of this session, you should be able to understand what this proof actually means and how it works. And so,
remind me one more time: the subscript here is the Spitzer notation or the Pearl notation.
So this is actually the Spitzer notation.
So this is the intervention is on smoking and tar here.
That's right. That's right. The intervention is, so I'm doing probability of tar given do cancer and do smoking times the probability of cancer given do smoking and do tar. And so like I said, we'll talk about that. But there's some things that you should already know, and that is the do calculus. So we're not going to get too much into the do calculus, but I do want to mention that there's this notation, there's funny notation, right? So cancer given tar, so a cancer is independent of tar given smoking and then you've got the subscript here, G, and you've got cancer smoking with a bar over it, right? And so I just want to explain what that notation means, because that's actually really useful to understand for everything else. So if we go back to so this is the rule that has just been applied, and the way it goes is this: if you have, and these are actually should be uppercase, because this could be a set of Y, set of X, and a set of Z, and a set of W. Okay, and the idea is this: is that if I have a probability distribution which says probability of Y given do X, and I'm also conditioning on Z and W, then I can ignore Z. That's why I subscripted this. That's why I colored that in blue, because notice that this is equivalent to this. That is, you can ignore Z if Y is independent of Z, given X and W, in a graph where we have removed all incoming edges from X. Okay, so that's what this X bar means here, is that it's a graph where we have removed incoming edges to X.
So does that mean is intervention, we intervene on X? Does that mean that if we are,
yeah,
if
exactly.
we are removing...
Normally the way that we indicate do X is that we remove incoming edges to X, right? So if we were to take a look at the graph, we have an original graph that contains X, Y, Z, and W, and remove all the incoming edges to X, and then we just do the D-separation question: is Y independent? Is Y independent, conditionally independent of Z given X and W? If it is, then we can just drop Z from this original probability distribution.
That's why it's called ignoring observations, because now you can ignore the observation of the value of Z. Although I want to remind, like that can be a confusing. Like these names of these rules can be confusing. Like so for example, in rule 2, you're taking that do Z and replacing it with just observing Z.
Yes.
But it suggests the direction, right? Like you always want to say in rule 1 suggests that you always want to be ignoring Z. If you finding ways to ignore Z, rule 2 suggests that you always want to find ways to convert do Z to Z. And that may not be the case. There may be you might have some kind of, like these are equations, so it might be useful for you in some proof of identifiability to go from probability of Y given do X and W to probability of Y given do X. Z and W because for example, you want to do something with Z in the next step of your proof. So
Yes.
it's always good to remember that like these equations go both ways.
Yeah. So this is really, so this is basically, you could think of it this way. If I have this pattern and it meets this criterion, then I can substitute this statement with this statement. Or, because as Robert was saying, if I have this statement and I have some Z that's not included in the observation that happens to be independent of Y given X and W, then I can add Z in there, just like what Robert was saying, right? So that's a really good point. So again, so this is action observation exchange, basically. I can swap out a do Z with a Z, or I can swap out a Z with a do Z, as long as Z is independent of Y given X and W in a different graph this time. This is a different graph. This is a graph where we've still removed incoming edges to X, but we've also removed outgoing edges from Z. So that's what this Z underbar means right here. If you can see the little underbar. I apologize for my LaTeX. This is notation. This is really hard to see. So does that make sense? Right. So where GX bar Z underbar is taken to mean the graph obtained from G by removing arrows pointing to Z to X and arrows leaving Z. Right. So that's a little different from the do X. Like do X, you know, if removing incoming edges, that has a very clear meaning. You know, that's like do X. This is something slightly different, right? Because we're also removing outgoing edges from Z.
We also use the do notation over here to indicate that there's an up. So like on the left hand side, we have like do X and do Z.
Yep.
There's no way to tell that if Z is incoming or outgoing, right? So for that notations. But on the right hand side, if we have that G notation, then it's clear, right? Which one is incoming, which one is outgoing.
Oh yeah, you can't tell from the joint probability distribution, but you can tell from the graph. So for every joint probability distribution, we have some graph that is faithful to all the independencies in the, or maybe it's the other way around. The probability distribution is faithful to the graph, right? All the conditional independencies applied by the graph, right? And if we have the true causal graph, then we claim that if we have the true causal graph, then and it turns out that Y is independent of Z given X and W, then you can swap a Z for a do Z or vice versa.
Yeah, it's just unclear. If we look at the left-hand side notation, we don't know which one is incoming, which one is outgoing, but the G notation makes that clear.
Yes, it's the graph, right? So there's
the graph,
in the graph. And the same thing here. So then the last one is ignoring actions. So you can just like drop a do Z, or if you thought about it from the other perspective, you can just introduce a do Z and it won't make a difference. And so that actually is a proof technique that's used in the identification algorithm. Because, well, for a variety of reasons, it turns out to be useful to add more do's because that actually simplifies the problem because you're removing edges, right? So if I can just remove edges, then I might as well, that simplifies my graph. So in this case, if Y, so you can drop Z if Y is independent of Z given X and W in a graph where you removed incoming edges from X and you also remove incoming edges from the set of Z nodes that are not ancestors of any W node in this graph, in the graph where you removed all incoming edges from X. So we'll go through this. I can actually show an example, not from here, but from here. So in our front door path, here we go. Here's an example of rule 3. So the rule 3, as you recall, and maybe I should just, so rule 3 is this guy. We're going to replace, so I'll just keep this here, and then we'll take a look at rule 3 here. So I say we have the probability of cancer, of tar given cancer and smoking. And what I've done is I've dropped cancer, right? I've just gone from probability of cancer, probability of tar given do smoking and do cancer, to the probability of tar given just do smoking. So I've ignored the action, right? I've dropped the action. And the reason why is because in this case, where can I, where's my, here it is. And the reason why, won't let me do it at the same time? There we go. No, it doesn't, and we keep snapping back down. Interesting. All right. All right, here we go. Okay, can you guys see that? So it says, if y is independent of z given x and w. And so here we have, as long as cancer, that's y, is independent of tar, that's z, given smoking, that must be x, in a world where we have removed incoming edges from cancer, that's x, and z, which is smoking. No. Oh, ZW. Z. Yes, no, that's right. That's right. No, wait. Cancer must be Z here. Sorry, because cancer is right here, and Z is right there. No. I just want to. Oh, this is a case where we don't have. It's unconditional, so we don't have to worry about X or W. We just have Y and Z. That's the problem. Okay. So we just have, well, Y, Z, and well, we should have Y, Z, and X. So Y is, in this case, tar. Z is cancer. And X is smoking. Do you guys see that?
Yeah.
Okay, sorry about that. It took me a little while to get that right. And then we apply rule 2, which says we can take probability of tar given do smoking and replace an action with an observation by saying probability of tar given smoking rather than given do smoking, right? And so as long as smoking is independent of tar, given a graph where we have removed smoking, removed outgoing edges from smoking. And look, here's the graph with outgoing edges from smoking removed. And then we ask, is smoking independent of tar? And the answer is yes, because of this confounder right here, right? Of this V structure right here. So not confounder, but because of this V structure, right? There's a collider here. So smoking is independent of tar in this particular graph, right? And likewise, cancer is independent of tar given smoking in this graph, right? It would be independent regardless of whether we had smoking or not, because there's nothing, you know, we've removed all the incoming edges from cancer and also all the incoming edges from smoking. Does that make sense? I have people nodding, so that's good. Do we have anybody shaking their head? Okay. So that's the do calculus. And so now you understand a little bit better about how the do calculus works. And now we're going to go on to Theorem 2. Or at least we're going to try to. So let's just go back to the paper real quick. There's the Spitzer and Pearl paper. So we've gotten from, so we talked about deseparation. We understand how deseparation works. We know what causal effect identifiability is. And now we're on to Theorem 2. The probability of y given x is not identifiable in the Beaux-Arts graph. And he gives an example where you have two causal models, M1 and M2, with that have the same. So these models, just to be clear here, there's a difference between a model and a graph. A model is these two models use the same graph, have the same causal graph, but they're two different functions that are associated with that graph, right? So remember, in a structural causal model, we can have every child is a function of its parents. And it can be arbitrary. It can be some arbitrary function, right?
Right.
Yeah. Okay. So if you have two models that have the same graph and the same joint probability distribution, then the question is it possible for their interventional distributions to be different? If it is, then in that case, it's not identifiable. So here we have a situation of the bow arc. And so the bow arc, just to remind folks, is this guy right here, okay? Also, looks like is this the bow arc? Yeah, here's the bow arc. And there's x goes to y. And we just ask, what's the causal effect of an x on y? And it says, it's just not identifiable from x and y, right, from the joint distribution. And so what they do is they actually provide a proof. They say, all right, let's create two models that are both consistent. We have two models, both with the same joint probability distribution and both with the same causal graph. You basically have u as a function of x. In the first case, y is a function of x XOR u. And the second one, y is always just going to be 0. Okay, and so then the question is, so if we can show that probability the probability of y equaling 0 is always going to be 1, right? Because if u equals 1, these are all Boolean variables, by the way. So u is a fair coin, and all three variables are Boolean, right? So if u is 1, that means x is 1, and u XOR and 1 XOR 1 is 0. And likewise, if u is 0, then x is 0. So 0 XOR 0 is 0, right? So y is always going to be 0 here. It's always going to be 0 here. But if we say what's the probability if we set x in this model so that we ignore the value of u, we just set it to whatever value we want, then it could actually produce a value of 1 for y. Whereas here, if we set x to whatever we want, y will always be 0. Does that make sense? So this is a proof that the bow arc is not identifiable, right? This is the situation where u is that both x and y have the exogenous variable of u, so they're both functions of u. Y is also a function of x, but here's a situation where the two models they produce different results, and but they have the same graph. Okay.
One question there is a part of the paper that says P is non-positive, or no that.
Right. So actually, that's a really good point, and they talk about that as well. So part of the rule of, was it not the do calculus? It was
below. It's in the page that you were.
Yeah, it was there, but there was they talk about positivity. And oops, positive. Yeah, here we go. Okay, so I guess the issue, I think the do calculus only works with positive probabilities. I think that's the issue.
You have that note also in your example in the bow arc.
Yeah. So they say, look, while P is non-positive, it is straightforward to modify the proof for the positive case by letting the fy functions in both models return 1 half the time, and the values outlined above half the time. So
but what does it mean is non-positive? It's just saying like in this case, the result is like you have probability of y equals to 0. I mean that's non-positive, is it?
Correct. So if the problem is that the probability of of y equaling 1 is 0, right? And I think there are a lot. So this is what they were said. This is what I was looking at earlier. Is that if you take a look at positivity, there's a sometimes it is assumed that the probability of observable variables is a positive distribution. In this paper, we don't make that assumption. Thus, we must make sure that for every distribution probability of W given Z, that we consider P of Z must be positive, right? So they're just like worried about corner cases, basically, right? In these corner cases, sometimes the do calculus doesn't do what you want when you have, zero, when you have non-positive distributions. Okay. Now we're getting to the meat. Oh, one really important thing. This is horrible. And so anyone want to give me an intuitive definition of what ancestor of Y means? And I'll tell you right now, it's a trick question, right?
I mean, the ancestor of Y in a graph is any node on an incoming path to Y.
Right, but not Y itself, right? And so Y is never an ancestor of itself, right? That just makes common sense, right?
Right, sure.
Okay, I would agree with you, and that is what intuitively it would mean. However, that is not what they mean. It turns out that when he says, we just assume the common definition for ancestor of Y, he's actually meaning Tian and Pearl's definition of an ancestor in Y, in which is that an ancestor of Y denotes the union of a set S and the set of ancestors of the variable in S.
Yeah, that's...
I'll just call that non-standard.
Yeah, it's a common issue. Like, same with Markov blankets. Like, does the Markov blanket include the nodes that is whose Markov blanket we're talking about, or is it excluded?
Yes. Well, this caused untold numbers of tears when I was trying to understand what the heck a C tree was when the definition involves this ancestor, and you interpret the ancestor one way and you have one graph, and you interpret the ancestor another way and you have a different graph, and they don't make any. It doesn't make any sense. So let's get to that right now. So we want to talk about a C component, right? This is kind of like one of the fundamental innovations that Tian made. Which is that if you've got some semi-Markovian graph, so a Markov graph is just a graph where all the variables are observable. A semi-Markov graph is one where you have these bidirected edges, right? And so the question is, if you just follow the bidirected edges from one node to another node, then and you try to, what they say is forms a spanning tree, but an easier way of thinking about it, let a path composed entirely of bidirected edges be called a bidirected path, right? The set of variables V that can be partitioned into disjoint groups by assigning two variables to the same group if and only if they're connected by a bidirected path. So, right? So that's an easier way of thinking about it in my mind, is that you just follow the edges. You follow the edges. You go from node to node, and you find out all the nodes that you can reach by just traversing these bidirected edges, okay? And so that is a C component. It's the maximal C component, is the largest set of nodes that you can reach from any other node. So if it turns out that all of those nodes that can be reached is the entire graph, then that graph is called a C component. So is that fairly clear? We can actually just kind of just go through and just check to make sure if we understand by looking at a bunch of examples. So what's the C component here?
It's just one, because
there's just one C component, right?
Yeah.
And here, what's the C component?
X and Z.
Yeah, X and Z. And then Y also gets its own C component. And in fact, that's what this says right here, is if I can zoom out. or actually I can move over. Yeah, the graph contains two C components, X, Z, and Y. So the joint distribution can be factored into one query that is in terms of X and Z, the other one that's in terms of Y. And this is the factorization. So probability of X and Z given do Y, and the probability of Y given do X and do Z. So that's from Tian and Pearl. That just being able, that factorization is from Tian and Pearl. So yeah, this one over here. This is also X and Z and Y are the two C components, and they have the exact same distribution. They have the same factorization, right? Okay. I think I've belabored the point. So now, what's a C tree? So if we let G be a semi-Markov graph such that G is a C component, then all observable nodes have at most one child. And there's a node Y such that the ancestor of G, using this funny notation of ancestor, is the graph, the entire graph. So the ancestor of Y is the entire graph. So obviously, a definition that did not include Y as the ancestor wouldn't even make sense there, right? Right. So if all the ancestors of Y, if the graph containing all the ancestors of Y is equal to the graph, then G is a Y-rooted C tree or a confounded tree. So,
Jeremy, I have a question.
yeah.
So how can the ancestors of Y be the whole graph? Because Y should be included in the whole graph, but Y is not the ancestor of itself.
Yes, you would normally be right, wouldn't you? But it turns out that they have a funky definition of ancestor, where an ancestor includes yourself.
Oh, okay, I see.
Yeah, and they do not say that explicitly at all anywhere in that paper, so there's no way you would know unless you actually check the reference to Tian and Pearl, where they do define what an ancestor is, and that's what this is right here. It includes S.
Okay,
Yeah.
okay.
I think in a normal graph, if we include the node itself as an ancestor, that means usually it's a root node, right? In a normal graph.
Yeah, this is a Y-rooted C tree.
Yeah, so, right. So if we, I mean, in computer science, usually when we say that a node itself also is an ancestor, then we know that it's a root node.
Yeah, if there's no ancestors yeah. Oh, if there's no ancestors.
There is
so this
like,
case, yeah.
So there is,
so the
if
root
there's
of a
an
node.
ancestor.
Yeah, it's confusing because and this gets all the computer scientists pissed off too, right? Because the way that they have defined a tree, the root of a tree is a node with no child. Which is the opposite of a computer science tree, right?
Right.
A computer science tree, a root is something with no parent.
Yep.
So this caused another week of complete chaos as we try to figure out what they meant by the root of a tree.
Yeah.
So yeah, correct. So what's the meaning of the root of a tree in this
so the
in this
root
context?
of a tree in this world that in this proof, in this paper, the root of a tree is a node with no child.
I think the thing is that the arrows are just reversed. In computer science speak, the arrows point away from the root, whereas in this modality, they point towards it and it's inclusive.
Yes. Isn't that? Yes, you've got it right. That's right, David. So this is why it's hard for a lot of people to understand Judeo-Pearl, simply because they redefine really commonly accepted terms.
Try philosophy, oh my God.
For no apparent reason other than it was convenient for them to to think of it that way. But yeah, it messes up every other computer scientist.
So the implication then is that what is special about the thing that has no children is that what does the directionality of the arrows represent in this model? What is it for an arrow to point to me as opposed to me to point to somebody else?
So if I point to you, that means that if you perturb me, then the thing that I point to will wiggle, right? Whereas if an arrow is pointing to me, then you can perturb me all you want, and the thing that is pointed to by me does not change at all.
Understood. Once again, that goes against the common understanding of ancestor. If my ancestor wiggles, I should wiggle.
That's true.
Yeah.
That is a true statement. That's true. That is the accepted definition of an ancestor, and except that I can. If you wiggle me, then I also wiggle, right?
Of course. No, that's fair. No, I understand.
Yeah. So, but if I wiggle, then my ancestors are not going to wiggle. My children will wiggle, but not my parents.
Okay, that makes sense. Yeah.
Okay. So yes, so I forgot about that additional tweak in the notation. Like I said, most of this talk is just explaining very simple and clear results, but having to rearrange the notation so that it makes sense and it is clear, right? All right. Where are we? So bow arc is not identifiable. Where is Spitzer and Pearl? D separate. No, we are at C tree. Okay, so this is actually really important. So notice here that Y is a node. It is not a set, right? And so we have a really nice result that comes from the situation where Y is a single node. And that is, well, first lemma 2, which is if you have the direct effect is identifiable if there is no subgraph of G that forms a Y-rooted C tree, right? So if you want to know the direct effect of the parents of Y on Y, then it's only identifiable if there's no subgraph of G which forms a Y-rooted C tree, right? So you've got, there's actually some examples of Y-rooted C trees. And figures 2A, D, E, F, and H are Y-rooted C trees. So let's take a look at those. A is a Y-rooted C tree. You see that? Because if you follow the node here, X is part of the C component, and its ancestor, all of its ancestors are also part of the C component, right? Now this is interesting. So I just want to make sure I understand this. So there's a node Y such that the ancestors of Y equals the G is a semi-Markovian graph such that G is a C component, right? So B is not a Y-rooted C tree, right? Neither is C, but D is a Y-rooted C tree.
I think figure A is the reason why we have to define it that the ancestor of Y is a
Sorry,
C.
say it again?
I think figure A is showing, or is basically the reason why you have to define that Y, the root node has to have a child.
Yeah. The root node has no child by definition.
I mean, yeah, has to have, yes, sorry, yeah, exactly. But it is the ancestor of Y in that graph to make it a C component, C tree, right, of Y. Right.
Sorry, say it again?
So I think A shows us that we have to define it that way, like you said just before, that Y is basically the root here.
Yep.
Having no child, but it's related. But I mean, the C tree of Y basically is still applicable here because Y has an ancestor.
Yes.
So basically, it wouldn't be possible if you don't define it based on ancestors, but on childs. I think that's just showing us that it has to be defined that way.
Yeah, it has to be
Like
defined.
David said, pointing the arrow is pointing that way, so we have to define it that way.
Yeah, we have to define ancestors including Y. Yes, absolutely. It doesn't
So
work
otherwise,
any other way.
otherwise A would have not been a C tree, I guess, of Y.
Yeah. Exactly. So this is not a Y-rooted C tree. This is not a Y-rooted C tree. This is a Y-rooted C tree. Is this a Y-rooted C tree? You want to take a guess?
So the ancestral nature
Yeah.
comes from the black arrows, right? Not from the dotted arrows.
Yeah. So the rule is that the graph has to be a C component, and the ancestors of Y form a C component, the same C component.
So my vote is that it is.
Yeah.
Yeah.
You
How about this one?
Find the spanning tree. Yeah, also.
Same.
Yep. How about this one?
Yes.
No, because you are not connecting Y.
That's right.
But so you're missing. Yeah, you're not connecting by directed. But
yeah. So that's I would say this is not a C component. This is not a C. This is not a Y rooted C tree.
For sure.
First of all, the entire graph is not the entire graph is not a connecting component, right? Because you got two connecting components, X, Z1, Z2, and Y. And second of all, the ancestors of this C component do not equal the C component. You know, there's two different C components, right? How about this guy?
Yeah.
Yeah, I think
yes,
it is.
It is. Yeah.
Yeah. Yep. All right. Just like I said, sometimes it just kind of helps to, if you can do yes, no, then you know you've got it, right?
So B, C, and G are the nodes.
B, C, and G are the nodes. Correct.
The nodes.
The nodes.
N-O,
yes.
N-O, not N-O-D. Sorry.
Yes. And A, D, E, F, and H are the yeses.
Got it.
Okay. Cool. So it turns out that the only way you can have something that's identifiable is if there's no subgraph of G which forms a Y-rooted C tree, if you want to predict the causal effect of Y. And it turns out that this is not true just of the parents, not just the direct effect. It's true in general. Let G be a Y-rooted C tree. Then the effect of any set of nodes, X in G on Y, is not identifiable as long as Y is not one of those X's. So we have a proof, right? So now, as long as our causal effect is only on one variable, right? We only know the causal effect on Y, then we have an identification algorithm already. Just check for the C tree and we're done, right? So there is, and they basically just do the same thing by generalizing the Bow-Arc graph, the proof of the Bow-Arc graph. I'm not going to get into it. You can read it, but the idea is that if you have this funny C tree, and you only have a single node that you're interested in the causal effect on, then you can take this home to the bank, right? You're done already. Just look for the C trees, right? The question now becomes, what happens if you have more than one causal effect that you're interested in? So Y is a set, okay? In the case where Y is a set, then, well, there's this notion of a C forest. Let's see if that works, right? So if G is a semi-Markovian graph where Y is the root set, now Y is like a root set, right? So that means all of Y has no children. Then G is a Y-rooted C forest, if G is a C component and all observable nodes have at most one child. So you can imagine, maybe we should
Yeah, some visual examples would help.
yeah, so some visual examples might be helpful here, right? So let's see here. Actually, not this. Not, where are those coming from? Oh, I see. Back up. Okay, here we go. So first of all, here we have a case where we have two Y nodes, right?
Mhm.
And in this case, we have a giant C component, right? And this, so these are both root nodes, and so therefore this is a C forest, right?
Yeah, and it is just because it has float. You have a set of nodes.
Right,
That's
it's a
different.
set of
The
nodes.
C3 and the C forest.
A C tree and a C forest, right? Whereas beforehand we only had one node. Now we had a tree, and now we have a forest, right? Now, interestingly, I think this is also a C forest, right? The only difference here is we've got this additional edge going from W1 to W2.
No, it's not, because you have two children. All right. The requirement was that you can only have one child node.
Yeah, you have W2 and X.
Ah, yes.
Okay, so essentially the way I see it is that you can have no crosstalk between your ancestors. Your ancestors can't talk to each other. If
Yes.
if there's connections between your ancestors, then the paradigm falls apart, because yeah.
David, you picked that up so quickly. Yes, you're absolutely right. This is not a C forest, right? This is a C forest, because that requirement that each node have only at most one child, right?
That's right.
Bingo. Okay. So it turns out that subtle difference between those two graphs makes one identifiable and the other one not identifiable.
Because the ancestors have crosstalk, you can't project up from Y. Yeah.
Yeah. Yeah. You got it. I mean, it's a little bit more complicated than that, but you've got, I mean, that's so, okay, right. So here it says, we'll show that there's just as there's a close relationship between C trees and direct effects, there's a close connection between C forests and general effects of the form probability of Y given do X, where X and Y are sets of variables. To explicate this connection, we introduce a special structure formed by a pair of C forests that will feature prominently in the remainder of this paper, right? So let's talk about a hedge. And so let's let X and Y be disjoint sets of variables. Let's let F and F prime be R-rooted C forests such that F intersect X is not empty, but F prime intersect X is empty. Furthermore, F prime is a subset of F, and these R's are a subset of the ancestors of Y in the graph where we've removed all the incoming edges to X, which could include Y. Then F and F prime form a hedge for probability of Y given do X in G. So the mental picture for this is as follows. We start with a C forest, F prime. Then F prime grows new branches while retaining the same root set and becomes F. Finally, we trim the hedge by performing the action do X, which has the effect of removing some incoming arrows in the difference between f and f prime, and that's the newly grown portion of the hedge. It's easy to check that every graph in figure 2 contains a pair of C-forests that form a hedge for probability of y given do x. And as you pointed, the graph in figure 1a does not contain C-forests. So figure 1a is this. Oh, so figure 1a does not well, now I'm confused. It says 1a. Well, let's go through the first part of that, right? So let us just check that we can find f and f prime for every graph in figure 2. So here is figure 2. So what's f and what's f prime? For this guy, f, let's see, how is f defined again? Okay, let f and f be R-rooted C-forests. We'll let, okay, such that f intersect x is not equal to 0, but f prime intersect x is the empty set. Furthermore, f prime is a subset of f, and the roots are in the ancestors of y, okay? So f is the one that does not contain x, and f prime is the one, sorry, f is the one that does contain x, and this is f prime is the one that does not contain x, right?
I don't know if we can do with that one, because it seems that in that small case, if the f prime will be the same as f.
No. Actually, in this case, this is I think the most helpful case, right? Because there can only be one f prime. F prime is the one that does not contain x, right?
Okay.
Right. So f prime has to be just y, because they both have to be y. They both have to be ancestors of y in the funny definition of y. So it can only be this graph right here, just y. Whereas f. So that's f prime, right? F prime does not contain x. F prime does not contain x. So then f must be the whole connected component here, the whole graph. So f is x and y, and f prime is just y.
So the claim is, the definition is that both f and f prime exist for any graph. Is that the implication?
F and f prime exists for every graph in this set here, in figure 2, because all these are not identifiable.
But in generality.
Oh, in generality, no. So in generality, this anytime. So the proof that we're not going to demonstrate is that once you have a hedge, then you know if you can form a hedge out of your graph, then you have something that is not identifiable. You define your x, you define your y's, you define your x's, you define your y's. You say, can I form a hedge? If you can form a hedge, then that causal effect, probability of y given do x, is not identifiable. So these are all not identifiable because we can form a hedge. And they didn't include all the ones that did. So there is another paper, I apologize. I go to psi wheel. Sorry, not that one, psi wheel. I go to causality. Spitzer. Complete identification methods for the causal hierarchy. So this contains 3 papers in one, basically. And as you can see here, they're figure One is his figure 2. These are the exact same ones. But then he has figure 2. These are all admitting identifiable effects. So none of these have a hedge in them. Whereas all of these do have a hedge.
But I still continue that figure A. Yeah,
Yep.
the graph in A.
Yep.
F prime and F are the same.
No, F prime and F have to be different. Because F prime...
No, but in the definition it says that both F prime and F, they don't have to have X.
No, that's not true. That's the difference between F and F prime. So the difference between F and F prime is that...
one is containing X and one is not.
correct. See, force, here's a hedge, right? So this is a slightly different definition. Be at F and F be R rooted C4 such that F prime is a subgraph of F. X only occurs in F. And R is an ancestor of Y in the graph where X incoming edges to X have been removed.
Ah, okay, yeah. I saw the sign different. Yeah.
Yeah, and here's the two differences, right? So here we have this contains no hedge for Y given to X. This contains a hedge. Okay, so let's take a look at the hedge, right? So what is the hedge for B? The mental picture for a hedge, right? So the figure in graph 3B contains a hedge for probability of Y1, Y2 given to X. The right generalization can be stated of, okay, right. So So I actually learned using this paper, but I thought it would be easier just to stick with the original paper. I'm now regretting that choice because the language in this is actually a little bit easier to follow. But I mean, they still have the problem with ancestors. So I mean, it's still hard to go through this. But now you have this is probably the paper to read. He just is slightly explains things a bit better. So you have a Y-rooted C tree. We have C forest. And we have subgraphs which form a hedge. Then, right. So then there's all these proofs. But before we get into the proof, so let's not bother getting into the proofs. What I wanted to show is what happens. Oh, so now now that we've defined a hedge, but let's first of all see if we can find the hedge in each case, right? I feel like that's really important. So the hedge here, F prime is Y, and F is the whole thing. Here, F is the whole thing. Well, no. So no, I guess Z.
No, you can't consider B, C, and G because they don't hold to the condition that the confounder can get to all nodes.
So this is R rooted. This is an R rooted C tree right here, right? And as long as Z is an ancestor of Y, then that's fine.
Okay.
Right? So Z here, so Z I guess would be the F prime, and XZ would be the F, right? Let's just go back to the definition real quick. There it is. A hedge. Okay, right. So let F and F prime be R-rooted C forests in G, such that F prime is a subgraph of F. X only occurs in F, and R is an ancestor of Y, right? So here we have Z is an ancestor of Y. So let's let Z be the R root, in which case we have two graphs, right? One is Z, and the other one is XZ. Note that any y-rooted C tree and its root node y form a hedge. That's helpful, right? So here, y and the C tree formed by, and the C tree here, this y-rooted C tree are f prime and f respectively. And likewise, y is f prime, and this graph, the full graph is f. You can't do that for this one, but you can do that for separately z1 and z2, right? So z1 here is a z1 rooted, I guess both z1 and z2 can be because it's R rooted, right? Where R could be a set. So this is a z1, z2 rooted C tree where z1 and z2 are the is the forest, and then is f prime, and then z1 z2 x is the is f. Do you guys want to try it for H? What's f prime in this case?
It would be y.
And what about f?
All of them.
Yep. How about this one? What's f prime in this case?
Z.
Yep. And what about f?
XZ.
Yeah.
Okay.
Yeah, you got it. Is everyone else following?
Yeah, you start to get confused a little bit.
You got confused?
Yeah. Can you repeat again what are in for example, in one of the graphs with f and then define again f prime? I got confused with that.
Yeah. So the idea here is that there are two C forests. Let's define what a hedge is, right? So let's go back to a hedge.
Yeah.
And we actually have two different definitions of hedge, right? We have this definition of a hedge, and we have this definition of a hedge, right? They're both the same. It's just one may be easier for you to think about than the other. So let x and y be disjoint sets of variables in G. Let f and f prime be R-rooted C forests such that f intersect x is non-empty, but f prime intersect x is empty.
Yeah.
Furthermore, f prime is a subset of f, and R is y or one of its ancestors in the graph where we've removed incoming edges to x.
Okay.
So that if you have this f and f prime, and there's a in the special case of C trees, right? So we remember about C trees where you only have one y.
Yeah.
Then it is always the case that the f prime is going to be the singleton root y, and f will be the C tree itself. The only time we have to get more fancy, go ahead.
Y will be always what? I didn't hear that. Sorry.
So f prime will always be the singleton root, just y by itself, just be the y node, and f will be the whole C tree itself.
Oh, okay.
Right? So if we go back here, well, that was it. If we go here, every time we see a C tree, this is 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 a C tree. In every one of those cases, f and f prime, the hedge is simply y and the whole graph. F prime is y, f is the whole graph. Okay, so we already know what the hedges are for these guys. And the only question is, what are the hedges for B, C, and Y and G? In that case, It's an R-rooted C tree, C forest. It's an R-rooted C forest. So this is an R-rooted, this is a Z-rooted C tree. This is a Z-rooted C tree. This is a Z-rooted, this is a Z1, Z2 rooted C forest.
Okay.
Yeah. And if we take a look at our original example, let's see here. We have, so this is not a C tree, right? Because of that edge right here. And well, actually, let's actually go to the algorithm now. We'll come back to this the difference between these two a little bit later. It's 9:30 now, so we're still actually doing pretty well in time. I'm about halfway done, and we're now actually ready to get to the actual identification algorithm itself. Okay. So before we jump to the algorithm, though, I just want to go one more step further, right? So I've said without proof that if you can find a hedge in your graph, then then it's no longer identifiable. And I'm still not going to prove it, but at least I'm going to show that there's a theorem that supports what I say, which is assume that there exist R-rooted C forests, F and F prime, that form a hedge for your probability distribution in G. Then probability of Y given to X is not identifiable in G. There you go. So if you can actually understand the following proof, then you are a better man than me. But I did want to show that that theorem exists, and that that using that knowledge, we're going to now apply the ID algorithm. Okay. How are you guys doing, by the way? Do you want to take a little quick breather? We've kind of learned a whole bunch of things, and do you want to take a 5-minute break, maybe? Or you want to keep
Sounds
going?
good. I want to take a bio break myself.
Yeah, want to take a little quick bio break? Yeah, let's do it.
Okay, 5 minutes. Sounds good.
Sounds good. 5 minutes. See you guys back at 9:36. My time, I guess, whatever it is time your guys is. All right. Talk to you soon.
I'm just curious, Jeremy, how long have you been working on this paper?
I can show you. So go to Confluence. Oh, I can't do Confluence here. Let me jump on. Hopefully this won't kill.
Oh, that's breaking. I'm just curious. No.
Oh no, actually I was somehow able to get in there. That's really interesting. They've changed the VPN rules. Here's my causality reading group. And we've been going since, well, we've been recording things since February of 2019, okay?
Wow.
And we got into the ID algorithm in April. And oh, yes, so actually, all right, so this was, so someone had actually implemented, no, I'm trying to remember when I actually implemented the ID algorithm, because that was right around that time, actually. So yeah, maybe it was like, I think it was in April that I implemented the ID algorithm. And then it took me a while to get everyone else on board so they could actually evaluate my code, because I just wanted someone to code review me. So I had to teach everybody how the ID algorithm worked, and I had to, I found an implementation, so it was just merely a matter of just porting it from Lisp, from Clojure to Python.
Right.
So, I was able to implement the ID algorithm without completely understanding it. So then I said, all right, let's see if we can all figure this out together.
So Jeremy, do you have the ID algorithm in Python? Can you share it?
Yeah. It's right here. And actually, it's a little broken right now because, of course, I tried to do some cool things, and yeah, it's a little broken right now. But I can show you. If you go to GitHub, actually, GitHub.com. Do I actually have it in COVID-19 causal reasoning? I might. Do I have it under why not? No. Oh yeah, I do right here. So if you go to github.com, COVID-19 causal reasoning, this is the identification algorithm right here. And it's a little bit of flux because basically I started off using PGMPy to represent everything. And then I realized that was a mistake. And then I went to SymPy because I wanted to represent these probability distributions algebraically, right? And that mostly worked, except for when we were trying to do things like sum over things. Then it didn't really like that. So then I had some issues with SymPy, but basically right now it's mostly implemented in SymPy. But yeah, this is the algorithm right here, and I've got a whole bunch of debug statements in there, so it's a little less clean than it could be. But yeah, this is the algorithm.
Nice.
Yeah, it's actually not too bad. So that's what we're going to go over now.
Jeremy, can you also share the notebooks from earlier where you had the notation clarifications in there?
Oh, yeah. And actually, I should probably add the notation clarification about a tree is not a tree in the computer science sense. So, yes. A tree is not a CS computer tree. So in computer science, a tree, the root of a tree has no parents, and the leaves have no children. In the Perlian world, the root of a tree has no children. And
yeah, that's always been a confusing part for me.
Right, the root of a tree has no children.
That's what you call a leaf in computer science.
Right. And it's still a tree structure though, right? Because you can have, just like you would have the root of, so it's just the issue is that the arrows point in the opposite direction. So it's still a tree structure. It's just that arrows are pointing to the node rather than pointing away from the root of the tree. Does that make sense?
What about the additional constraint that there can be no crosstalk between ancestors? Is that part of the definition, or is that a
I think that's just an observation you made that I think is going to be borne out to be true. We're just going to confirm that when we actually get to the figure 1 in the paper.
Not my interpretation of it. The definition was that only that all the children could only have at most one child, right?
That's right.
Yeah, and that's part of this definition. So a tree has that constraint.
Yes. It has only one child, whereas in computer science theory, the root of the tree has no parents, and the leaves have no children, and all children have only one parent, right?
Right.
The root of a tree has no children. All nodes have
at most
and all right. The root and all nodes have at most one child. Yes. Right. So you just swap parent for child and it'll all work. Okay. So X's are really your, the X's are your leaves in this world. Because you can always cut incoming edges you can always ignore incoming edges to X. Okay, so yes, I will share this. I'll put that probably in the why not? Yeah, I'm just going to save it there. It is, and actually I should probably rename it to be something like rename notebook, annotation notes. Okay. All right. And then it's actually possible to download a project. So maybe I'll do that as well with, so I finally figured out projects in Causal Fusion. So you can have multiple projects and you can associate a bunch of different graphs with each of them, right? So my identification examples were being drawn from Causal Fusion and other papers. So it was just getting too much. Then I just created another one that just focused on the ID algorithm. And so I will download those and make those graphs also available for people. And while you're at it, you might want to know that there are all of these pre-canned examples in Fusion that range from identification to recoverability. So this is recoverability using sample selection bias, transportability. So now you've got these transportability nodes, G-identifiability, which gets into things like hedgelets and thickets, which are not part of the standard literature, and then Verma constraints. And so so it might be useful to that's just something else I just discovered when I was messing with Causal Fusion this morning.
Is that all new, I wonder?
I think that is. I think a lot of this is new. Yeah, some of it might have been around for a little while, But yeah, he keeps adding to it. It's really impressive. So yes, I can just download all those graphs, and I'll just make that available as well.
Thank you.
Yeah. There you go. Awesome. All right. All right, it's 9:47. Shall we get back to it?
Sure.
All right. So I might be switching between, his original paper and the Spitzer and Pearl paper because they actually give slightly different explanations, and I think both of them are useful. So I'll just kind of, if something doesn't make sense, I'll switch to the other one. And plus, I have really nice notes in here. So. Still sticks with the do notation though, I think. Yes. Yeah. All right. So let's take a look at the function, the ID function. Okay. So what did I say here? So all right. So the input is x and y, so the thing you're intervening on and the thing that you want the causal effect of. P is a probability distribution. G is a causal diagram. It's a mixed graph, right? So contains both directed and these bidirected edges. And the output is either going to be an expression for the adjustment formula for the probability of y given do x in terms of the observable variables, or a failure which returns the hedge, the f and f prime. Okay? So let's just go through this algorithm. We take a graph, we take an x's and y's, we take a joint probability distribution, and the first question we ask is there a causal effect? If x is empty, well then just marginalize over everything that's not y and you're done, right? Now you've got the probability of y. So that's easy enough, right? If no action has been taken, the effect of y is just the marginal of the observational distribution on y, right? So that's the simplest case. Now, what happens if there are some nodes that are not ancestors of y? So if we're interested in the effect on y, it is sufficient to restrict our attention on the parts of the model that are ancestral to y, because descendants of y are just noisy versions of y, and variables that are neither descendants nor ancestors of y have no useful information to contribute. So we can just like prune those parts of the tree, and then so that's what we're gonna do. So we're gonna return a reduced version of the ID. We're gonna call the ID algorithm again. This time we are going to keep y, but we'll subset out anything that is. We'll just keep the intersection of the ancestors of y with the original x variables, and we'll go ahead and we'll marginalize out any variables that are not in the ancestors of y, and then we'll just return the graph that is not the ancestor, that's just the ancestor of y, right? So that's line 2. That seems pretty straightforward, right? Let's take a look at line 3. So now we say, okay, let's let W be all of the vertices that are not x, and then subtract off from those vertices any vertex that is an ancestor of y in the graph where we have removed incoming edges from x, right? So if we didn't do this last part, then this would be already have been taken care of here, right? But since we're looking for ancestors of y on a new graph, then there may be some w's left, right? And the idea here is that this simplifies the graph by removing those arcs from the graph that do not affect the overall answer. So, right, so the idea here is that this is actually rule 3 of the do calculus. So if you just want to take a look at rule 3 of the do calculus, what do we say here? Ignoring actions. Oh, no, sorry, not ignoring. So it's actually rule 2. it's action, observation, change. So the idea here was, is that right? Is it union? Yeah, I just want to make sure they got this. Yes, union. So what they did is, remember, we are, if W, so basically what they're saying here, the way of saying this is that, identification notes, here we go. If Y is, basically what they're saying is that you can replace Z. Oh, no. It's actually action. It's actually, no, it's not ignoring observations. Do Z. I was going to say that this is like one of the rules of the do calculus, but I don't actually see the rule that it actually is. But what it's doing is it's basically saying, if I have a W that's not an ancestor of Y after we remove the X's, then you can just toss those W's into the do X, and that will simplify things by removing all the incoming edges from W as well, right? Now I'm getting silence, and I'm not sure if it's because you guys are like, yeah, of course, or if you're like, what did you say? You want to give you a hint as to which way you guys are going?
So I understood 1 and 2.
Okay. Okay, so let's take a look at 2 again, right? So 2
take
says,
a subgraph. It's creating a subgraph. It's trimming off the extra stuff you don't need to create a graph which has specific properties that we care about.
Yes.
And then that's passed into 3, and then 3 is opaque. So
no, it's not passed into 3. So what's going on now is you call the ID algorithm with all those things pruned, and now yes, you pass 1, you pass 2, so now you get to pass in the recursion. You get to now to step 3, right?
So this is recursive. Okay, that was not obvious.
Yeah. See this ID here? It's calling the ID function with just a different set of variables, right? So yeah, that's probably the first thing, is that we're now just going to call ID, but we've reduced the number of variables. So yes, essentially, yeah. So
this would have fully completed the entire deep dive of the recursion before it returns to 3.
Yes.
And what comes back is the list of subgraphs.
No, is a probability distribution.
Well, no. So, let's just assume that we've passed line 1, right? Because if we didn't pass line 1, if we activated line 1, right? If this passed, or if this check passed, then we would be done, right? So obviously 1 is not. So obviously our inputs, if we get past 1, then we now ask. Well, actually, I guess it could be possible. It could be possible that if you call the ID algorithm after you've removed all the ancestors, if there are no ancestors of Y that are, the X is not an ancestor of Y, then this will be the next thing that runs, and you'll be done, right?
Correct. But I think it cannot run through 2 again, basically.
It can't run through 2 again. That's right.
Yeah. Unless you have done something wrong in 2.
So okay, but now, so right. So let's suppose we've just executed 2, and now we come back here. We pass 1, we pass 2, and now we get to here. And this wouldn't pass, except that we're not asking about, right? So we just check to see if there are any non-ancestors of Y in V. And now we're asking if there's any non-ancestors of Y in V, in the graph where we have removed incoming edges to X. So that changes the graph, right? So it's possible that something could have just gone through 2 and then come back, and then there's still some W's here, okay? And so the point is that it moves those arcs from the graph that do not affect the overall answer. So basically these W's don't affect the overall answer. So we might as well remove them. We might as well just toss them in the X, because whether you do X or you just or you don't do X, sorry, if you do W or you don't do W, it doesn't affect the overall answer. So you might as well do W so that you can remove the incoming edges from W. Just makes the graph smaller, right?
Sure.
I mean, the claim is that W isn't going to affect the overall answer. Do you believe that?
Okay. I can imagine a case in my head, but yeah, you're just filtering and making sure you can simplify the graph.
Yeah, that's right. We're trying to simplify the graph, and so we can do that by by removing all incoming edges from W. Okay, so now here comes the hard part. So now what we're going to do is we're going to check to see. We're going to take a look at the graph where we've removed all the x nodes. Okay. And now we say, in that graph where we removed all the X nodes, what are the connected components? How many connected components do we have? Okay, and there's two possibilities. The first possibility is that there are several connected components. Okay, or sorry, C components, confounded components. There could be several confounded components. If that's the case, that's great, because Tian and Pearl proved that you can always factor an interventional distribution in terms of these C components. So we'll run the ID algorithm separately on each of those C components, and then we will multiply them all together and then sum over them, sum over all the vertices that are not in U, X, or Y, and we're done. So we can decompose the problem into a set of smaller problems using the C component factorization of causal models. If the entire graph is a single C component already, then further problem decomposition is impossible, and we must provide base cases. Okay, so the first possibility is that we can decompose this. The second possibility is that we can't decompose this, right? So if that's the case, then we say, all right, let's check to see what the connected components of G are. Okay, whereas beforehand we were just saying G without X. Now if we say, if the connected component of G is G, then we have our F and F prime, right? We have our F, which is this, and our F prime is the connected components without X. So we just return those. Right, so
and why fail? So you're, what does the fail represent? Is that an exception that throws you out of the deep recursion because you found the answer? Or?
Exactly. Yeah, throw is like an exception. So you try this, and if
you return the hedge.
You return the hedge. That's right. You return the hedge.
Yeah, because if it's a hedge, yeah, it is not identifiable.
Yeah, I think 5 is basically the hedge. I think you're doing the hedge in 4, and you walk further, and because when I mean what they say in on the page 1230, one page before basically.
Right.
Oh, just on the left side. No, just sorry, on the left side. They're drawing this mental picture just below the definition. And they're
this one. Mental picture for hedges as follows. Right.
Correct. And I think they're basically telling you to finally walk where you trim the hedge, and then that's step 5, and the mental picture where you start with the C for S F prime is basically 4.
Mm-hmm. I see. So this part right here is 4. This part right here where you're removing you're trimming the hedge.
Correct. I think
Yeah.
so.
Yeah. So we're looking at, oh, right. So we're right. So basically trimming the hedges by performing action do X. So right. First, so we start with a seed forest F prime, right? And that's what this is right here. This is the seed forest without X in it, right? So that's the small one. Then F prime grows new branches while retaining the same root tree and becomes F. That's this guy right here. Finally, we trim the hedge by performing the action do X, which has the effect of removing some incoming arrows in the part of F that's not in F prime. That's the newly grown portion of the hedge, right?
Yeah.
And so if you find that, then it's then basically if you have this hedge, then you're done, right? You formed a hedge. So that was the point, is that this algorithm says if you have a hedge, then it's not identifiable. This algorithm says here's how you build up a hedge. Here's how you form a hedge from your graph.
Correct.
Cool. Yeah. And then so the first case is that if C of G of X is if you have a hedge, you're done, right? But if this S is an element of your connected component of your overall graph, then you actually have an answer right here. You can just so that then you actually have an identification. So you just return your factor distribution.
Yeah, that's basically the first possibility, the first option, that you return an expression for P.
Well, it's the second one, because this one also returns an expression.
Oh yeah.
Right. But yeah, so this is the second time where we have an opportunity to return an expression for the ID algorithm. That's right, for P in terms of P of X, P of V, I mean. So now, if it is not an element of C of G, and so let me jump back here, oops, to here. So if there are, so we first checked here, so if the graph itself and the subgraph do not contain any X nodes are both C components, which is sufficient, that's sufficient to conclude the graph and the subgraph form a hedge, which by theorem 17 means that it's not identifiable. So we got that. Now we say if there are not bidirected arcs from X to other nodes in the current subproblem, then you can replace probability of Y given do X with probability of Y given X and thus solve the subproblem. Okay. So you can imagine if there's a bidirected edge from X to any other node in the current subproblem, then you cannot continue, right? But if that's not the case, then we can, if X is not, X is not part of your connected component, that means that probability of Y given do X is the same thing as probability of Y given X, and you can just solve it directly. Does that make sense? Taking from the sound that it doesn't make sense. All right. So let's see if I can maybe show, well, maybe, okay, so the last part is the most complex, and I'm not sure if we haven't quite figured out 6, then let's hold off on 7, and maybe we could go through an example. Okay?
Okay.
Does that seem fair? Right. So here we go. So we explain why each line of ID makes sense. Conclude by showing the operation of the algorithm on an example. Okay, we talked about line 3. Let's talk about line 6. Asserts that if there are no bidirected edges from X to the other nodes in the current subproblem under consideration, then we can replace acting by conditioning, right? So that is rule. Which rule is that? Action replacing action observation change. That's rule 2. So the claim is that if there's no bidirected edge from X to the current C component, that means that X is independent. Z, yes. Z is independent of, so Z in this case is our X, right? So if the thing that we're performing do on is independent of Y, which we know it is if it's not in the C component, then we can convert do Z into Z. Or in the case of Spitzer and Pearl, we can convert do X into X. And that's what they're saying. We can, right? So if there's no bidirected arcs from X to other nodes in the current subproblem, means that this current subproblem is the confounded component. And if X is independent of that confounded component, then you can replace do X with X. Does that make sense?
Basically, because we stripped away the whole, or because it's not a C forest, so we can assume that rule 2 applies. Is that correct? So is that too simplified?
So remember what we said about Tian and Pearl, that if you can we can always factor a joint probability distribution in terms of the C components, right? Sorry, joint interventional distribution in terms of the C components. So you can say C component 1 times C component 2 times C component 3, right?
Yeah.
And so the claim is that if all your X's are not in the current C component that you care about,
Correct. Yeah.
that means that X and the C component are independent, right? They're conditionally independent of each other, right?
Yeah.
So therefore, I can replace do X with just X.
Because you made sure that all those components are separated already.
Yes.
By doing all the steps before.
Yes, all the steps before, exactly. So I've just checked to see if this S is an element of my C component, then I can C without X, right? If there are no right, it's C without X, right? So that's what S is. S is C without X. So for that particular case, I can if X is not, X is not in the current C component.
That applies for 1, 2, and 3 as well, right? It's just a bit more complex in 4, no?
We just haven't gotten to this case yet. I mean, 1, 2, 3, and 4 are asking simpler questions, and they're kind of removing things before you get to it, right?
Yeah.
Yeah. Okay. So now we get to number 7, which is kind of a beast. All right. So we partition X into 2 sets. We take so the first set is W, which contains the bidirected arcs into other nodes in the subproblem, and Z, which does not contain any bidirected arcs into other nodes. Okay. In this situation, identifying probability of Y given do X from P of V is equivalent to identifying probability of Y given do W from probability of V given do Z. Since probability of Y given do X equals the probability of Y given do W do Z. So we've partitioned out W and Z. Now we're considering 2 different do's. but the term probability of V given due Z is identifiable using the previous base case. So we just need to consider the problem of identifying probability of Y given due W. Right? So if we split up things into a W and a Z, then the Z's already been taken care of right here. So all we have left is that W. So they're saying if there is not if there's an S prime such that S is a subset of S prime, which is and S prime is in our connected component graph, then return. So this is basically you're just getting rid of Z, right? So it's not so obvious. I apologize. And it's just messy here. It's like hard to even see what's going on. So I don't know. Let's see if what they say if they say exactly the same thing or if they say something slightly different. What do they say? Figure 7 or line 7. Okay, we got that. That's great. And is there another one? Yes. Next. Okay, that's triggering. So we're just going to go through it. ID always terminates. I mean, I don't know if it's easier. Maybe it's easier to take a look at the code to see how that's actually implemented because the notation is almost impenetrable, right?
That would be great, actually.
Yeah.
I'm wondering why is step 6 happening before step 7? It's like you're trying to work with the same set, and then you divide it into a smaller subset. But that means you have to have a problem in 6 that you're actually reaching 7.
Well, don't forget this is a recursive algorithm, right? So once we have identified multiple S's, then we run the ID algorithm separately on each of those S's, where each S is a confounded component, right? So,
but in 6 you return a value, so basically you end the recursive function.
So this bottoms out, right? And now you return to the function that called it, right? And the function that most likely called it is this one right here, where we're calling ID in parallel across all of the connected components.
Oh, okay, I see. Yeah, okay. Okay, got it. Because you have a multitude of S's, and that's why you need to parallelize and see in every single one if you have an identifiability there.
Yes.
Correct.
Yes.
Got it. That's why it's also a bit more. The ident is a bit lower, right?
Sorry, what was that last bit?
Because the ident, it's idented 5, 6, and 7. There's an ident there because it's basically steps below 4. You're still running in 4, but you call 5 and 6 and 7.
Exactly. But you're again, each time you call ID, you're running it on something on a smaller part of the graph, right?
Yeah.
So you're still reducing the problem each time, and that's really the trick. It's this divide and conquer, right? Eventually, things will either bottom out at here, or here, right? And if it bottoms out at fail, then the whole thing is not identifiable. But if it bottoms out at 6 and 1, then you just multiply all those things together, and you're done. You have your answer.
But wait, I still have a bit of a misunderstanding in 6 to 7.
Yes.
6 is assuming that I'm having a subset S.
So
let's
go back to S, right? So S is S1 through SK is a set of connected components, right?
Yeah.
And furthermore, you don't even get to step 5. I mean, if you, right, so the first, right, so okay, hold up, I take that back. So there's two possibilities, right? One is that that when you take the connecting components of the graph without x in it, that results in a bunch of C components, right? So each of these is a different C component. In which case you run ID on each of those separate C components. The other possibility is that there's only one C component. In which case you have to check, first of all, have I formed a hedge? If you have not formed a hedge, then that means that the C component of this C is actually not
6. Okay, I got it. 6
this
is basically which basically 6 is just checking if you're in 4A or 4B. In which case are you? Did you split up S into multiple smaller S's, or do you only have one S, one set?
No, this is so 4 does that, right? 4 says, did I split up my is my the C of G? This says check to see how many C components I have, and if I in this modified graph, and I'm going to return a whole bunch of C components, right? But in the case where I only return one C component, I do have to make one more check, which is to see whether or not the C components of the full graph is the full graph itself, or if it's something smaller. If it's the full graph itself, I have a hedge. If it's something smaller, then I just need to see if S is equal to, if this S here is an element of the C components of the full graph. If it is, then I'm done. If it's not, then what I'm asking is there some S prime that is an element of my connected graph such that S is a subset of it?
Oh, so you're making it actually, you're extending the.
So okay, so I think it helps to remember that this is a set of sets, right? This is a set of vertices, right? Sorry, so I said set of sets, but I actually meant set of. This is so C of G. If C of G is just one, okay. So actually, let's see if I can. S here is a set of vertices, right? And we want to know if this set of vertices is an element of my connected of the C components of the full graph. Well, hold on. What is S exactly? I can't remember if it's a set of sets or if it's just but that makes a difference, right? If it's a set versus if it's a set of sets. Here it's a set of sets. That's very clear. Here it's just a set of nodes. Or is it just a singleton node?
I think it could be a set of nodes.
Yeah, it could be a set of nodes, right?
I think S is generally a set of nodes, and you can, and 4 tells you basically if you can split it up into several C components, which basically also contain different set of nodes.
Right.
The first case would be in 4. You have several C components. Sets of nodes.
I just figured it out. So if I do the if I call this function giving it the graph without x, that can return a set of sets, right?
Correct. Yes. And
If I call
yeah.
If I
Sorry.
call C of G, it could return a singleton. It could return a single set, or it could also return a set of sets, right? If it returns a single set, then I have a hedge. If it returns a set of sets, then if one of those sets is S, then I do this. Otherwise, I have to check that maybe there's one of the sets in here that this is a subset of.
Yes. I think the difference between 6 and 7 is that you have basically constructed different sets of C forests, and each individually you need to check if it's identifiable or not. In case 6, it would be an identifiable UC forest. In 7, it would not.
No,
Well,
this
it could be. It could be, but it needs to be checked again based on the hedges in 5.
Yes, that's right. That's right. It needs to be checked for hedges. That's right. Because, yeah. So would it help to actually go through an example where you were actually executing this algorithm?
Yeah, it would be great. Yeah. You have one?
Yes. Well, I do. So I have both code that does it, and I also have words that do it. So I'll start with the words, but I can show you the code. Maybe it makes sense to show the code first. I don't know if the code will actually help though, because it just looks like the. So we're at line 7, right? So I go S. S prime is find superset. Is, yeah. So it's basically just saying in programming language what the math said, right? So I think it might actually be helpful to actually go through an execution. All right. We give an example of the operation of this algorithm by identifying probability of y1, y2 given do x from probability v in the graph shown in figure 3a. So let's just remind ourselves what figure 3a is. It's this guy right here. It's figure 1a in your paper. Okay. So the intuition for this is you've got some mother who's been pregnant mother who's been infected with an illness, and you want to provide some kind of treatment, and you want to know what the effect is of that treatment on both the mother surviving and the child surviving. So this is a pregnant mother. So this is whether or not the child also gets infected with the illness, and whether or not he or she survives. So in the first case, so in this case, the chances of a mother, so there's no causal effect between the mother getting the illness and the child getting the illness. In the second case, the mother can transmit the illness to the child, or maybe protect the child. It's just some causal effect, right? Whereas in this case, they're not uncorrelated because there's some common cause, but we can't measure that. So the point is that this is not identifiable and this is identifiable. So we're going to go through and see, go through the ID algorithm by checking to see the causal effect of X on Y1 and Y2, okay? So, since the graph is equal to the ancestors of Y1 and Y2, and since the the C components of the graph without X is equal to G, and W equals, so the W that they talked about here, or no, sorry, this W is equal to little w, is equal to W1. We invoke line 3. Right, since there are, so we do have an X, and since there are no vertices that are not ancestors of Y, we get to line, and since it's the case that W is non-empty, then we invoke line 3, okay? And attempt to identify probability of Y1 and Y2 given do X and do W, okay? So now we go back to the top of our algorithm, and we've got two, and now the connected component, the C component of the graph without X and W in it is equal to W1 and, okay, so this is where it gets confusing. It has this thing called W2 to W2 to Y2. So that's not actually a thing. And in the other version, where they go through it, they do not do that to us. Yeah, so here we go. Now is equal to, yeah, so once we have this, we check to see what the connected components, the C components of G without X and W are, and that results in this set, Y1, W1, and Y2. So we invoke line 4. If you recall, line 4 was here. So we see that when we do, remember X is now X and W, and so we have several things. We don't have just one thing. So now we invoke line 4, and we return the ID algorithm separately on let's see, it's Y given do, yes. So probably Y given vertices minus each SI. Oh, you're actually right. Oh, this is interesting. So where'd it go? So, oh, no, we're not doing first. Before showing the SI's complete properties, we do the following operation of the algorithm, right? So we invoke line 4. Thus, the original problem reduces to identifying. So when we invoke line 4, then we've now reduced the problem to identifying the causal effect of Y1 given do X, W1, W2, Y2 times the probability of W2 given W1, X, Y1, Y2, and probability of Y2 given X, W1, W2, and Y1. Do you see how we got from here to here? We were basically able to do separate ID algorithms for Y1, W2, and Y2. Does that make sense?
Yeah.
Cool. So solving for this, and notice that even though we're solving for this W2 here, we eventually marginalize it out because we're ultimately interested only in Y1 and Y2. So solving for the second expression, that's this guy right here, we trigger line 2. Noting, so line 2 says, are there any V's that are not in the ancestors of Y for this particular graph? And actually, I wonder if it might be easier. Well, okay, we'll just go through this, and then we'll go through the automated proof. So for the second expression, we trigger line 2, noting that we can ignore nodes which are not ancestors of W2. So therefore, W2 reduces to this the probability of W2. So probability of W2 given do W1, X, W1, Y1, and Y2 simply reduces to the probability of W2. And why is that? Because W2 has no ancestors, right? W2 has no ancestors, so all the things that we're doing to it aren't gonna affect it. It's just you can just marginalize it out, right? Oh, wait, sorry. Okay, I'm gonna go back to the other one here just because. So we look line 4. The original problem reduces to finding this, right? Solving for the second expression, we trigger line 2, noting we could ignore nodes that are not ancestors of W2 and W and Y2, which means that this reduces to, oh God, they do things differently here. Sorry, let's go back to here. Trigger line 2, noticing that we can just simplify this to probability of W2. Similarly, we can ignore non-ancestors of Y2 in the third expression. So this is the probability of Y2 given do X, W1, W2, and Y1, right? Oh, sorry, in the first expression, sorry, first expression. So we were looking at probability of Y1 given do X, W1, W2, and Y2. But the point is that we can ignore any non-ancestor of Y1. So that means that third expression obtains just probability of Y2 given do W2. So that this simplifies to this. Then we conclude at line 6. Line 6 was, oh yeah, right here.
That's the second option of identifiability.
Yep. So we conclude with line 6 to obtain the probability of W2, sorry, of Y2 given W2 is equal to the probability of, the probability of Y2 given do W2 is equal to the probability of Y2 given W2. Okay, so that part is done. But now, solving for the first expression, we trigger line 2 also. Obtaining this is equal to this. The corresponding G is shown in figure 4A. 4A. So right, so here we are. We are now trying to predict probability of Y1. See if I can get them both in the picture at the same time. Here we go. So solving for the first expression, that's this guy. We note that Y1 is only dependent upon X and W1, right? So we can just get rid of W2 and Y2. So that's simplified. The corresponding G is shown right here. So after we do this, then this is the graph. Next, we trigger line 7, reducing the problem to computing probability of Y given W1 from probability of Y given X and W1 times the probability of W1. The corresponding G is shown in figure 4B. So finally, you trigger line 2, obtaining the probability of Y1 given do W1 is equal to this expression. So now we've got the full first expression taken care of. So putting everything together, we get probability of Y1, Y2 given do X is equal to summing over W2. We have probability of Y2 given W2 times the probability of W2, which came from here. And this part right here came from here. And then this last part right here comes from here. Okay. That was kind of intense. Do people have questions?
Good job.
Yeah, so what we can do, oh, so this should be identifiable, right? No, which one? Yeah, this one should be identifiable, right? So let's see. We go, yeah, here we go. Probability of y1, y2 given do x, and he just gets exactly what we just had here beforehand, right? Probability of summing over W2, you get the probability of y2 given W2 times the probability of W2, which came from the second expression, and this one came from the first expression. So let's go take a look at the derivation. How did he do it? Notice that he does not do it in terms of the ID algorithm, right? What he does do is he does it in terms of the do calculus. Okay, so here he says, well, probability of x, probability of y1, y2 given do x is equal to probability of y1, y2 given do x and w1. And the reason why is because in this graph, when we cut all incoming edges from W1 and X, then W1 is independent of Y1. So if it's independent of Y1, then we can just we can just ignore actions, or we can create actions. We just created an action, right? So this is rule 3. We can just create actions arbitrarily if we know they don't matter. Here we go. Rule 3 was rule 3. Rule 3 says we can ignore actions, or we can just create arbitrary actions, right? We can start with this, and we can create do z if y is independent of z given x and w in this graph right here, and that's exactly what they did.
So, Jeremy?
Yeah.
The first part of line 7.
Yeah.
I mean in the paper, in the ID algorithm function.
Uh-huh.
It's the first part. The first part is basically comparable to rule number 2, no?
Oh, that's a good question. Part of 7? Let's go take a look at that. So here's the algorithm. Rule 2 says if you remove the ancestor, rule 7, this one right here.
I mean, yeah, and the first part.
So, okay, again, we've got some. It's hard to interpret in terms of do calculus, but obviously it's possible because Elias Barenboim did it, right? So they're saying here, let's partition x, just x, this x right here into 2 sets, right? Those are W, which contain so x has been split into W and Z, right? So, if we partition x into 2 sets, those that contain bidirected arcs into other nodes in the subproblem, and those that do not, right?
Correct.
Okay, so in the case where we want to predict probability of y given do x from P of V, the claim is that that's equivalent to saying probability of y given do W from probability of V given do Z. Because probability of y given do x is equal to probability of y given do W times do Z, because we split these things out. That's just because we split x into W and Z. But the term probability of V given do Z is identifiable using the previous base case. So we just need to consider the problem of identifying y given do W. So
that second, that last sentence is basically following the further recursive or when you further recursively apply the ID algorithm. It doesn't follow from step 7.
All it's saying here, I think, is that these take care. So if we split x into w and z, then this is the z situation, and this is the w situation.
Exactly, yeah.
And since we only have to worry about w's, we'll remove all the x's that are not w's.
And that's essentially what rule number 2 is saying, no?
Rule number 2 says if there are any non-ancestors, then we can remove that from the graph, right?
I know. I'm not referring to.
Oh, sorry. Do rule 2. Sorry.
Yes. Yeah.
Do
sorry.
rule 2, which says that if I can remove, yes, I can remove dues. Yes, that's actually, no, being able to remove dues is actually rule 3, right? Because if I can ignore an action entirely, I can just drop it. Then that's rule 3.
Yeah.
This one says I can transform a do into an observation.
I think it's comparable to step 7, but
yeah, I don't know.
I'm still trying to wrap my head around it.
Yeah. Well, that's why I wanted to go through the fusion, causal fusion, because they're actually using the do calculus, and then we might be able to get a simpler solution, right? Yeah. So first of all, he's saying that probability of y1, y2 given do x is equal to the same thing as probability of y1, y2 given w1, given do w1 do x, right? And that's because we can just arbitrarily add w1 to the do using rule 3. And we just proved it here because we can see that w1 is indeed independent, conditionally independent of y1 and y2 given x in this graph, right? This graph that you see right here, which is the graph of w1 and x with their incoming edges removed. So next thing we do is we simply sum over w2. Okay. So you can always sum over w2 because we've got y1, y2 here, and we can just add a new variable but then sum over it, right? So that's not a problem.
Yeah.
But then from here, we can represent this in a C component form. So let's check this out, right? So this says that I can write probability of W2, Y1, Y2 as, given do W1X as probability of W2 given do all these guys times the probability of Y2 given all these guys times the probability of Y1 given do all these guys, right? And let's see why that's true. Because what are the C components? The C components are, what's this non-active? I don't know what that is. So W2, this looks like one giant C component to me, right?
Isn't it exactly the same what we just did in line 4?
Is that the same that we did in line 4?
Yeah, I think so.
Let's take a look at line 4. Yeah, totally is. You just decompose the problem into a set of smaller problems using the C component factorization. So that's totally 4. You got it.
So they are actually using the same, like causal fusion is actually using the same.
Yeah, it's using the ID algorithm underneath, but it's just doing it in terms, but it's just explaining it in terms. It's the difference between inference and explanation, right?
Yeah.
Inference, you use the ID algorithm. Explanation, you use the do calculus.
Yeah.
Isn't that cool?
I wonder if, inference. So they have some inference algorithms.
They're using the ID algorithm underneath.
Yeah.
They're using the ID algorithm underneath, but then they have this explanation engine that generates a human readable, in terms of the do calculus, domain specific. So an explanation. I mean, I've been doing program traces, right? So if I want to understand what's going on in my ID algorithm, I do a program trace, and all these guys are hedges. So they're not going to work. But if I go here, then I have a program trace. Well, in that case, it didn't. Oh, that's pretty quick too. Where are my?
Oh, you mean like a debug? Oh, this kind?
Yeah, exactly.
Yeah.
I actually go through each of the. I generate each of the intermediate graphs and perform the computation, all that kind of stuff, right? So yeah, like line 3. So like when I go through here, a graph hedgeless for probably y given do x. I actually go through here and show I execute line 3 and then execute line 4 and then identify and then I go to line 2. So this is a program trace. This is not an explanation, right? This is not using the domain language that somebody who's not intimately familiar with the algorithm would understand. This is an explanation because it's using the domain language of the do calculus.
Yeah.
That's what's so brilliant about it. The difference between a program trace and an explanation is like really clearly demonstrated here. So yeah, so then we apply rule 3. And then we split this up. So now that we got this, we can just split this up into 3 separate problems. We solve each separate problem separately. And then we get our expressions in all 3 cases, and we multiply them all together, and we're done.
Yeah.
Okay, and it's 10:48, so we actually finished early. We actually got through all that. I don't know. I mean, like I said, I can show you the code. I'm not sure if it's going to be all that enlightening for you, but I can certainly make it available to you. I'll go ahead and put that on the COVID-19 causal reasoning GitHub. But you guys have any questions?
Great. I think I'm the only one left. Get a few.
Oh my God, you're right. Everyone else left. They're like, screw this, man. I have no idea what you're saying.
That's great. I will definitely look into your code.
Yeah, I'll put the link on the Slack. No problem.
Yeah.
Well, thank you for sticking all the way through it, Bernard. I think I scared everyone else away, but
no, thank you, man. Thank you, Jeremy, for preparing all that. It's great. I think it's nice to see to understand the internals and the foundations.
Yeah.
If you can relate to that, that's very valuable.
Yeah, I think so. I mean, it's like I said, it definitely took a while to understand this stuff, but now that we can do that, then it becomes much easier to understand like all these advanced papers that I was showing you, right? With like the causal fusion. If we go to the library, he's got all these. He's got these books. Oh, this is great. So causality, all of the identifiability algorithms in that I think he does with the do calculus. He doesn't use the ID algorithm because the ID algorithm was published after causality. So that's the other thing, is that a lot of people have read causality and they're like, oh, I really understand causal inference, but they have not kept abreast of all the cool, really amazing developments that have happened since causality was published. And they're not talked about all that often.
What date is it? When is that? Our paper from today. What was the release date?
Like 2008.
Publishing date.
Okay, so here's the crazy. No, it couldn't have been that late. It was definitely. So 2002 was when Tiananmen Pearl was published, and I think. Do you guys remember when Daniel Pearl died? Like he was executed. Do you remember that? He got beheaded on television.
Yeah, I heard about it.
So that was his son.
Yeah.
And so he took like a leave of absence at that point, and that's when Ilya Spitzer worked out the ID algorithm. So he came back and he was like, "I've got this complete algorithm for you," and he's like, "That's like the best thing you could have possibly done for me." So he proved that the Duke calculus was complete, and had an algorithm that proved it, that actually calculated it for you. So. Yeah. So yes, you can imagine how Judea was like, "Oh, this is a nice little shining moment in a really bleak moment in a really bleak time." So, so things like Z identifiability, which not only predicts causal effects from observational distributions, but you can have other interventions as well, and you have your target intervention, and you can say, "Can I predict causal effect of my target distribution from these additional interventional distributions?" And that's typically the case in biology, is that we don't just have observational distributions, we have lots of interventions that we've performed as well, just not the intervention that we want to perform. And the question is, can we somehow combine and infuse all that data to get something that was identifiable that was not identifiable from any one of them by themselves, right?
Yeah.
So this gets into causal fusion, but yeah, I feel like in order to understand any of this stuff, you need to be able to, and transportability especially, where you have these additional nodes, and then most recently this G identifiability. So let's see, where is he? Those are papers. Are those different ones? Oh, let's say that's from books. That's why. So fusion examples. Yeah, he's got all these G identifiabilities. And so, this is like the most general form of identifiability where you can combine all kinds of things. And we only did probability of Y given do X, but there's also probability of Y given do X and Z, right? Where Z is not due, but you're basically, now you're doing ID on a conditional distribution, right?
Yeah.
And then you can do the same thing for counterfactual graphs. So that's what Spitzer and Pearl, this Spitzer and Pearl right here do. So they do this not only for the ID algorithm, they do this for IDC. So here's ID, and then it's just a few pages later IDC, and basically it's just like we just add this slight modification, then call ID, right?
Mm-hmm.
And then if you want to do counterfactuals, it turns out that you just add this additional function called make CG, which kind of compresses your twin or triplet world graph into a counterfactual graph. That's what this is right here. And now you call ID again. That's it. So, and then this G identifiability, they identify a few more data structures like hedgelets and thickets, but basically it's just like one additional step of knowledge, and then you understand what a hedgelet and a thicket is, and now you can understand what the GID algorithm is. So yeah, so taking the time to have learned this will help you so much. Yeah, so here's IDC, ID star. It's basically just ID. Yeah, you just call ID star. So it's just the same. It's even simpler. And then IDC star is just, slightly different from that. So yeah, once you've got ID, now that you've got ID under your belt, then you've got access to a whole lot more algorithms. And and then I forgot to mention causal effect. GitHub.
You mean the package? Mm-hmm.
Yeah, so there's one, yeah, exactly. So if you go to id.r, this is the R implementation of exactly what we just saw, right? There's line 1, there's line 2, there's line 3, there's line 4, there's line 5, 6, and 7.
Oh, I see, yeah.
You now understand how this stuff works.
It's great.
Yeah.
Maybe you should build up on what you just showed.
Yeah.
Maybe basically C identifiability or some variations of those, because you laid out the foundation now, basically the
Yeah.
ID algorithm, and we could probably build up on this.
Yes. I very much want to. I actually been funded to develop a causal inference engine, and this is the basis of it, right?
Yeah.
But
Depends on what the other ones are.
One thing I just go ahead. Yeah. So yeah, we have this, and one thing that this guy did, he didn't just implement a bunch of algorithms. He created a couple himself. And one of the issues that I ran into when performing these kinds of analyses is that we can get like these enormous expressions, right?
Yeah.
And it's because, but whereas Spitzer and Pearl says this is the causal effect of probability of y1, y2 given do x, this is what I get from Whitmore, and I get something even larger when I do it, right? Because we're not simplifying these expressions. And so what this guy who wrote Causal Effect did is he also came up with algorithms, that's his PhD thesis, was how to simplify these symbolic expressions so they look more like this.
Yeah.
And so adding that simplification in there will actually make it really quite tractable. And I would love to implement this for like Pyro, right? You run the ID algorithm and you say, okay, now I just need to compute this empirical marginal.
Yeah, because I remember Raoul was saying we're getting the probability distribution out of the ID algorithm. That's not the case in that. From that perspective, you just basically getting the expression how you can compute it, right?
Mm-hmm.
And it could be.
Yes, you get an estimand. You don't get an estimate.
You're not
still
getting,
have to estimate it.
Correct, yeah. And so you have to implement it somehow in.
Yeah.
In I mean, you need to connect it with your data, so you have to connect it somehow into. You could connect it into Pyro somehow.
Yeah, that's what I'm saying.
Yeah, that
would be very interesting. And if you're interested in working on that, then with me, then we should talk.
Sure.
Right on.
I'm very interested into this. The only thing is always the time constraints.
Understood, right? And this is why I haven't implemented more than just the ID algorithm, right? Like I wanted to build up a community of people who actually understood what it is that I did so that we could all work on it together.
Correct. That's a good start, at least. Yeah. Yeah, we can do that. I think we should just focus on probably the next reading group and work out our or probably understand more of those foundational algorithms before we can start implementing. But I'm very interested in it. Sure. So.
Thank you, Jeremy. I'm saturated for today.
It's very inspiring to see basically how things are working underneath, because I mean I was already using stuff, parts of it, but I was just applying it. But now that I understand it, it's definitely helping you to transform ideas into something more meaningful.
Yeah. I feel like now we have the tools. We actually understand.
Correct.
Yeah, you can look under the hood. We looked under the hood.
Yeah. Correct.
It doesn't seem quite like so much magic anymore, because it can feel very much like magic. So it's
in the beginning, yes, yeah. You look at it, and I think the most difficult part is probably to cluster all those separate methods and materials and papers in your head, that you know what is a graph manipulation, what is basically identifiability, and what is connected to all those different topics.
Yeah. Yeah.
Great, Jeremy. Thank you for preparing that and guiding us through it.
My pleasure.
I unfortunately have to drop off.
Me too. My wife would be very happy that I'm leaving at 11.
I guess so. Your daughter as well. I hope the cucumber is found from last week.
Yeah, we just got to figure out what we're gonna do for next week is the real question, right?
Correct. Yeah. We can probably ask in the channel, because since everybody else has dropped off.
Yeah.
We should.
We should. Yeah, exactly. We should make a decision ourselves anyway. So yeah.
Yeah, and then we can also talk about the paper we want, or that article we wanted to write together.
Yes.
We can do that next time as well, probably. Yeah, it would be interesting. I'm very interested in next time, as usual, Saturdays, best days
Awesome.
in the week. All right, Jeremy,
All right.
take care.
All right.
See you next time.
Next time.
Bye.